Hello everyone. In this lecture, we are going to discuss the lower sum, upper sum, how it is bounded when your function is bounded on given partition AB. In the previous lecture, we have seen the definition of upper Darboux sum, lower Darboux sum, oscillatory sum, partition, refinement, common refinement, all those things. Now in this theorem, you are given that the function from closed interval AB, who is real valued, is bounded functions. That means the f value lies between two fixed numbers. That numbers are finite throughout the interval AB. Now if P is any partitions, let me denote the partition by this. Initial point is always your initial point of the interval, x1 greater than x0, x2 greater than or equal to x2, and so on, xn minus 1, and last point is the interval last point. So this is the partition. I will just denote the notations, and then I will call rth subinterval of this partition by this xr minus 1 and xr, and I can take r equal to 1, 2 up to n. Since points are n plus 1s, we have r subintervals there. Since function is bounded, so function has supremum and infimum on the closed interval AB. So here small m and capital M, this is infimum of f on closed interval AB, and this is supremum of f on closed interval AB. So that you should keep in mind. And later on, since it is bounded on the interval AB, I can see, suppose this is your interval A and B, and you have so you may have increasing or decreasing function. I will take both the case, okay, like this, increasing and decreasing in the region, and I am taking the partitions like this, partition of this interval. Okay, these are the points on each subinterval. Since function is bounded on closed interval AB, you can see what is the value of this function. The highest value of function, suppose it occurs at this point, or you can see who is the peak point of that. So this is the capital M, and since it is cutting to the x-axis, so 0 will be the, okay, if it is 0, okay, then it will let it be. This is the supremum of the functions, and every value of the function lies between these two on y line. Your y values lies between these two numbers for closed interval AB concern. Now xr minus 1, xr is the r subinterval. On this interval, you can see this is the highest value, or you can create any not this much, you can take any random interval of this. I am not taking as capital M value here. Okay, I am taking this interval as your rth interval. So the position of this is xr minus 1, and it is maximum value, so I can call it as mr minus 1, and position of this is xr minus 1 and mr minus 1, because in this interval we can see this is the infimum of the function f, and in this interval you can see this is the supremum of the function f. So I have to denote all these notations. So let mr denotes the infimum of the functions on particular rth subinterval of closed interval AB, and let capital mr denotes the supremum of the function on that ir subinterval. Keep that notation in mind. And in this interval, you can see what is the relation. If I compare this mr and capital Mr, we can see, since this is supremum value in subinterval IR and this is infimum value in subinterval IR, so this is always less than or equal to this. Is always less than or equal to this, and length of each interval, this delta 1, delta 2, it will be your delta R. Just multiply by a fixed number, that delta R here, that constant number, inequality remains same, and then making the summation of all these, from all subintervals, you can see this value becomes LPF and this value becomes UPF. So we have verified this. What we have verified? The lower sum is always less than or equal to upper sum. And in short, we can say that the oscillatory sum of that partition is always non-negative, because UPF minus LPF is always greater than or equal to 0. From this one can write UPF minus LPF is always greater than or equal to 0. Now for the remaining part, I am going to write next. I hope this understood to you. I have to show that LPF and UPF is bounded by that two numbers, and how they bounds found I will write there. Okay. Now on only subinterval IR, on subinterval IR I am writing. On subinterval IR, we just now verified that MR is always less than or equal to capital MR. And keep in mind that your M is the infimum throughout the interval. Same diagram I will plot here. Okay. Or what I will do, I will not take values intersecting to by axis. I will take increasing, decreasing, any functions you can take. So I will take this function. This is at point B and this is at point A to better understand of this. So this value is your small m, that means it has position A comma m, and this is your capital M. So what you did, you want to do partition of this interval. Let anywhere there is R sub interval, we can locate the supremum of that function f on sub interval. It will be denoted by capital MR notation, and small mr will denote the infimum of the function f on that closed subinterval of this AB R subinterval. So see, among all the infimum subinterval and infimum the interval, it will be always less than or equal to that infimum of subinterval. So here you must have this, because among all this m is the smallest value. It is particular smallest value in the earth. If it is the smallest value for all throughout the AB, then equality holds, otherwise strictly less than. And this we verified for R subinterval. Now this is another figure. So this value is your MR and this value is your capital MR. And on the real line we can see the comparison. M is less than or equal to MR, less than or equal to capital MR, and less than or equal to M. So this is less than or equal to M, because supremum, that M is the highest for all. Now at last interval, the Mn and that M may be same, that's why equality is written. Then later on, what I am going to do, I am multiplying just the constant fixed number delta R to each. And it is true for when I took R equal to 1, R equal to 2 and R equal to n. It is true for. So I am writing all those inequality and summing the corresponding for R equal to 1 to n, R equal to 1 to n, R equal to 1 to n, R equal to 1 to n. So since m is fixed number, the summation of all subinterval is okay. I will write what is the summation of delta R. We also make remark in the previous lecture that this plus this plus this plus this plus this plus this total is b minus a. So this has to be b minus a. So summation of delta R, m is constant, m sum of all delta R is b minus a. By definition this is LPF, by definition this is UPF, and this is m constant and summation is b minus a. So diagrammatically I can also show you here. Okay, this is the proof of this. Geometrically we will discuss in the same figure. Try to understand this proof geometrically. Now what is m into b minus a? This length is b minus a and this height is m. So this is the area of rectangle, this rectangle, that m into b minus a. Next, capital M into b minus a. This is capital, this height is capital M and this length is b minus a. So I will shade it by another color. This is the area of that. So you can see the area of this rectangle and area of this rectangle is always have highest value. Now look at for each subintervals. Look at for each subinterval. Okay, let me draw diagram for the subinterval again. The same diagram I will consider. Okay, I will do it for only 4 points: x0, x1, x2, x3. You can generalize it. Okay. So what is this value? This is your m1 on the first subinterval, and this is your capital M1. So this area is nothing but m1 into delta 1, this much length. This length is delta 1, this length is delta 2, and this length is delta 3. There are three subintervals. Next, I am just calculating the lower sums. Okay. And what is next? This is the last rectangle. So this is LPF for corresponding 3 points, 4 points return partition. The sum of these, and you already constructed earlier one, this m into delta minus a. This is m and this is b minus a. So not delta minus a, this is b minus a. This area and area of these three. So okay, this is okay, this is extra portion, this is extra portions. So that's why this will be less than or equal to LPF. This shaded region is LPF, and this is your m into b minus a. Now likewise, now LPF is always less than or equal to UPF, that we have seen geometrically always as well as in the result also. So UPF will be shaded by the black color. So this is your UPF. This is your UPF. This is your UPF, and you can see UPF is greater than of this, because at this much area is your LPF, and this is the extra term. And at last you are going to find, don't forget about original graph. Your graph is like this. Okay, at last the value here, this area value is the capital M multiplied by b minus a. So this is the larger one. This is the larger one among all these three terms. This is m into b minus a. The blue shaded is LPF, black shaded is UPF, and this is the larger version. So geometrically also we can prove. I have taken only 4 points. It can be generalized for n plus 1 points. Okay, in the next lecture we'll see more properties about this upper Darboux sum, lower Darboux sums. Later on we want to define the Riemann integral concept also. Till then, watch the previous videos. Thank you. Subscribe the channel.